Hey everybody, welcome back. This is 14.6. We're working on triple integrals for Calculus 3. Today we're learning how to deal with cylindrical and spherical shapes. So let's start off with cylindrical. We got a cylinder over here and we can break it up into little flat discs and go up the disc. So it's almost like working in polar for each disc. We can see we swing out an we go out a distance R1 to R2. We're rotating an angle theta 1 to theta 2. We got this block in region. And then we're up a height delta Z. This looks a lot like the polar, because the polar is just the 2D plane down there. Now we're just adding a Z component. I did want to show you something we have in Canvas. Go take a look at it. If you go to your file section down here on the left bar, and you scroll down, you will see triple sphere. This is triple integral, spherical, cylindrical. So here's a little image of what we're doing with cylindrical. We've got this cylindrical wedge, and we're looking at a single block. And we looked at in polar how we got r dr d theta, just doing the 2D range, and now we're adding in a delta Z. We also look at this picture when we get to spherical in the latter half of 14.6. So refer back to this picture as well. We will see though that we're going to get rho squared sine phi d rho d phi d theta. Okay. So we'll be back to this. Back to cylindrical. So if we're going from R1 to R2 for any given wedge or any given region, and theta is theta 1 to theta 2, and Z is Z1 to Z2, we can have this cylindrical block somewhere. We can write our function f of r theta z. It's really the limit as n goes to infinity of f of r k star, theta k star, and zk star, where it's based off a point on a block. We saw that this delta V is really, we talked about it a second ago, it's literally a cylindrical thing. So a disk times the height. So we're going to use polar regions for each disk. Then we slap in the height component. We recall we had R, delta theta, and now we got a delta Z. Doing the limit as n goes to infinity, makes it an integral, and that good old r dr d theta shows back up. And the only difference between that and polar is now we're swapping in a dz component, and we have a z integral. Okay. So we could do z as a function of two heights. So a first boundary and a second boundary. They could be functions of r and theta. So we could write our triple integral as the region in the polar section with a z component doing two different heights. And so this is theta, this is r, this is z. This is one setup that's common for doing cylindrical integrals. We do z first, then r, then theta. Theta tends to be pretty boring. It's just sweeping out a loop. We do it last. R tends to depend on theta though for weird shapes. So steps, we need to identify what those Z1 and Z2 are in terms of R and theta, not X and Y. And then convert to cylindrical if they're not already in that form. And then we need to sketch the projection R of the solid on the XY plane, just like we did with the regular triple integrals, how we projected onto the plane that's we've integrated the other variable through. This will help us do our limits of integration. Our next videos are on examples, so peace.